Bingo! The timer for us has started. Okay, so we've exited the part of the course where we write down exact closed form solutions to answers. And, it was really cool. Super good to know about how all this stuff works. And now we're trying to give ourselves the vocabulary for being able to iterate to a solution. So when you can't just write down that closed form solution, can you get closer and closer as you iterate a mapping, for example? And so that's the notion of a sequence. So a sequence will be any set of vectors indexed by the counting numbers, yet it's still perfectly fine if you start out at -100 and go forward. You just can't go backwards and forward. That's the only thing. It can't be infinity in both directions, okay? So you need one direction going forward, and then you have a sequence. Typically, we put the curved brackets around it, the braces. Sometimes we use the curly brackets, the braces. The first concept with a sequence is what does it mean that all of its elements get closer and closer to a point X. That's called the limit of the sequence. So a sequence converges to a point X if you give me an allowable approximation error, no matter how small. I can give you a number that maybe depends upon that approximation error, but it's finite, such that as long as you go out at least that far in the sequence, the approximation between the value of the sequence and the limit is less than the approximation error you gave me, okay? So it's all about getting close. So that's the notion of a limit. Xn is approaching X as n goes to infinity. And sometimes this notation is just too heavy and we just simply write Xn goes to X. Or sometimes we'll put n goes to infinity under the bracket, but it's pretty clear. We'll spend a little bit more time today on Newton's algorithm, but it was just used last week as a way of generating a sequence of approximate solutions to this set of nonlinear equations. So there's 4 equations, 4 unknowns. We're wondering, does there exist an X that it solves that equation? And Newton needed to do that, and he invented a little algorithm. And it's written right there. We'll see how it's derived. Maybe you already read the handout. And here we took a really brilliant initial condition and then converged to high accuracy to the solution. Okay, so that's the notion of a sequence. Here we just developed 16 elements, but in principle we could have iterated to infinity. Okay, so today we're going to just warm up and talk about limits being unique, how to use sequences to characterize a closed set. And remember, if you understand closed sets, you understand open sets because a set is closed if and only if its set complement is open. So if sequences can characterize closed sets, they tell you about the topology of your norm space. And then we'll get into this issue that I hinted at on Tuesday of last week, that the problem with a convergent sequence is you have to know the limit point a priori. And clearly here, we have no idea what the solution is, and we have a good guess now, but it's still not the solution, okay? So is there actually a solution? And that will lead us to the notion of a Cauchy sequence, and eventually to something called a Banach space. And so, I don't know, dead white men, okay? So it's, I'm not trying to make a political statement, believe me. But I just thought it's kind of fun to see these guys, okay, Cauchy of Cauchy sequences, Stefan Banach, who introduced the notion of complete normed spaces. Hilbert, if your norm comes from an inner product, you're working on a Hilbert space. He's considered one of the, I think, greatest ever mathematicians to have lived. We saw the Cauchy-Schwarz inequality. There's Hermann Schwarz. We've still not done the real numbers, and we probably won't, but if you ever want to read about how the real numbers are actually constructed, Dedekind did that first. And we use infinity all the time. It's a symbol. We like it. We talk about n going to infinity and stuff like that. Turns out there's multiple infinities, okay? There's the infinity of counting numbers. There's the infinity of the real numbers. I think today you're kind of predisposed to believe that those are different sizes of infinity. But when Gregor Cantor was just understanding that and introducing those ideas to the mathematics community, they thought he was a fool and completely wrong. And they eventually shunned him, and it drove him insane, literally, okay? So it doesn't happen just in art. It can also happen in the sciences. And he was right, okay? He was absolutely right. But anyway, don't let us rejecting you drive you insane, okay? Stick to your guns, go for it. Okay, so sequences. Any questions you want to pose just before we get started? Unfortunately, I don't have any other dead people to put up here. And I don't plan to join that rank anytime soon. So maybe there'll be a Rob 501 student up here 100 years from now. How about that? Okay, enough for the morbid jokes. Let's just do a little warm up then with sequences just to get us going. So first proposition. If xn converges to x and xn converges to y, then x equals y. In other words, limits of sequences are unique. Okay? Are unique. There's only, if there has a limit, there's only one. Okay. Why should that be true? Well, here's an idea. And we'll see if we can turn that into a proof. Let's check how far apart x and y can be. Let's see if we can estimate their norm. Well, the nice thing we can do is we can add and subtract something and not change the equality. And then we can use the triangle inequality okay, so then the idea is, well, if xn converges to x, this is getting small as n goes to infinity. If xn converges to y, this is getting small as n goes to infinity. Okay, so this goes to 0 as n goes to infinity. Hence, it has to be true, okay? Now, that's not very formal proof, but it's clear what the idea is. So let's just turn this into a formal proof, and then we'll be warmed up on sequences and the definition and applying it and stuff like that. Okay, so here's the formal proof. So let epsilon greater than 0 be given. Because xn converges to x, there exist n of epsilon such that for every n greater than or equal to n, the norm of xn minus x is less than, say, epsilon over 2. If you want to put epsilon here, that's fine. We'll just get epsilon and 2 epsilon here. It doesn't really matter. But the same thing also holds true here. Xn goes to y. There exists some other constant. Could be, maybe it's converging more slowly to y. Maybe it's converging faster. Okay, but it's finite. Oops, this one was finite as well. Such that for every m greater than or equal to m, the norm of xm minus y is less than epsilon over 2. Now we just let L equal to the max of m of epsilon and n of epsilon, and the max of 2 finite numbers will still be finite. Then, for every little l bigger than or equal to L, we'll have that the norm of x minus y less than or equal to the norm of x minus xl plus the norm of xl minus y less than or equal to epsilon over 2, and that's epsilon. Okay? Okay, so why does that imply that the norm of x minus y is 0? Because 0 is the only real number that is less than or equal to every positive real number. Okay? So, yes, I should have put this down before I put down my little square bracket. Now we're done. Okay, so the difference between the two limit points is actually 0. Okay, just using the definition of converging sequences. You go far enough down the path, everything beyond that is within your given level of approximation. That's the notion of convergence. Okay. Questions on that? No? Okay, another little warm-up act, and then we'll get into the Cauchy sequences. Definition. Let P be a subset of X. Okay, so be a subset, and X in our big norm space. Then X is a limit point of P if there exists a sequence X sub n satisfying, and there's two properties here. All of the elements of the sequence are in P, and then the sequence converges to X. Okay, so X is a limit point if I can construct a sequence of elements of P that converge to X. So square root of 2 is a limit point of the set of rational numbers because I can do a decimal approximation of it, okay? So that's the notion of a limit point. Now, is there any notion we've covered that this seems kind of close to? You know the answer, but you don't want to say it. Okay, got it. I gave you the hint already. It's the notion of the closure of a set, okay? So proposition X is a limit point of P if and only if X is an element of the closure of P. Okay, so mostly these notions of limit points you'll see in papers and stuff, but mainly I'm doing this just to make sure that we can recall the definitions of these properties, and then once we have them, that's really simple steps to prove these. So if you have this sequence that's in P, and they're getting arbitrarily close to X, what is the distance from X to P? 0.7? 1 over 100? Or 0? 0, right? You can approximate X arbitrarily closely by elements in P. So X, the distance of X from P is 0, so X is in the closure of P. Okay, so that's one direction. We'll write it down. But if X is in the closure of P, what does that mean? Well, it means for every epsilon greater than 0, I can choose an element of P such that it approximates X with error epsilon. So what if I choose my epsilon to be 1 over n? Then as n gets bigger, my elements are getting closer and closer to X, and I have a converging sequence of elements of P. Okay, so it's just really writing down the definitions here. So let's just do that. Okay, so if X is a limit point of P, there exists a sequence xn such that for every n bigger than 1, xn is in P, and xn converges to X. So that's the definition. So let's now just unwrap the definition of convergence. Conclusion, for every epsilon greater than 0, there exists an n of epsilon finite such that for every n bigger than capital N, the norm of xn minus x is less than epsilon. Okay, so that's just unwrapping this. So now we have elements of P that are arbitrarily close to X. Let's see. Here? Oh, that's supposed to be less than infinity. Yes. Thank you. I can't even call it a copy and paste error, right? But my brain did a copy and paste error. Okay, thank you. So and so this means the distance from x to p equals 0, and that implies x is in the closure of p, okay? Because we've characterized the closure of p as the set of all points whose distance from p is 0. Okay, let's go the other way around. Suppose x is in the closure of p. Then the distance from x to p is equal to 0. I want to construct a sequence. Hence, I'll take my epsilons of a special form. Hence, for every n finite, there exists an xn in P such that the norm of xn minus x is less than 1 over n. Okay, so the distance from x to p is 0 means for every epsilon positive, I can find an x in p such that the distance is less than epsilon. So I just specialize my epsilon to the form of epsilon equals 1 over n. Okay, so I can generate arbitrarily small elements. Conclusion, xn goes to x. And xn is an element of p for every n. Therefore, x is a limit point. Questions, answers, curiosity? Okay, so just thinking ahead, the final exam is 4 weeks from now, roughly, something like that. It's on a Monday, 4 weeks from yesterday or something. There's no big proof on the final exam because I don't want to grade them, okay? They're little mini proofs, like 2-liners, okay? And the 2-liners will be things that you basically unravel definitions and then that gives you what you have to do, okay? So I'm just practicing that. When you look at the example finals, you'll see what I'm talking about. I mean, I haven't written this one, but I'm just guessing that I'll put something like that on there and Niels will help me find some interesting but straightforward things, and they're all like this. You take the definitions and you unravel the properties and then you get the next one if you understand the definitions. Okay, so it's worth doing those, okay? So that's what's going on here. Okay, so as a corollary, a set P is closed if and only if P contains its limit points. P is closed if and only if P contains its limit points. X is in the closure of P, so if and only if X is a limit point. It's the same statement, but what you see written in all the books is this one right here. So limit points help you characterize the notion of a closed set, and once again, set is open if and only if its set complement is closed, so you can characterize all of the open and closed sets with limit points. Yeah, you're about as thrilled with that as I was when I learned it. Okay, fine, it's pretty straightforward. But it warmed us up on the definitions. That's all we're trying to do. Okay, so here, let's get to this point of limits and sequences and converging, okay? So every time we're talking about convergence here, I have to know the target limit point a priori so that I can check that my elements in my sequence are accumulating near x. So I have to have x in hand in order to make such an estimate and see that it's less than some epsilon. It doesn't have to be 1 over n. It was convenient for us there. So drawback of the notion of a converging sequence is that you have to know an a priori guess for the limit in order to check norm xn minus x goes to 0, okay? If I don't have x, I can't compare it to the elements and see that they're actually getting close to that value. So if I'm just creating an algorithm and I want to show that the algorithm, when I iterate, produces in the limit the answer to my problem, I'm stuck. I don't have the x in hand to check. I just can't do it. So as an engineer, we need another way around this problem. And what's really weird is that, you know, it was this guy, Cauchy, you know, around 1930 or something, 1830 or something, who figured out this idea that us as engineers need to have these converging algorithms, okay? So, what was his idea? What was his idea? So here's the big definition. Come on. Definition. A sequence xn is Cauchy if for every epsilon greater than 0, there exists some number n depending upon epsilon that's finite, such that whenever n and m are both bigger than this number, the terms in the sequence are getting really close together. Okay, so put a little star next to that one. Super important. Okay. Okay, so why is this different than the definition of a converging sequence? There's no limit in the picture, okay? This is something I can check on just the elements of my sequence. I don't need the candidate limit point. Now, it could be that, yeah, I can write down lots of conditions that only depend upon the thing, and they're completely worthless, okay? So this one is studied because it's not completely worthless. It's got a lot of value to it. But the main point is I can check this condition because it only involves the elements that I am generating, okay? So this depends only on the elements of the sequence. Okay? You do not need to know, which is really guesswork mostly, a candidate limit point. Okay, so that's the idea of a Cauchy sequence. The terms in this sequence get closer and closer together as you go farther and farther down. They start clustering around one another. Okay? Notation, we sometimes write xn minus xm goes to 0 as n and m go to infinity. Okay. Okay, so question, is this a necessary condition for a sequence to converge? So if a sequence converges, is it automatically Cauchy? So is this a necessary condition? Okay. Can you guys see in your head the estimates you might want to make? Okay, so proposition. Come on, select the colors. If xn, let me just write it like this, it's shorter. If xn goes to x, then xn is Cauchy. Okay. What's the idea? It's really the same proof that we used when we proved that limits are unique, except we changed the names to protect the guilty here. How far apart are the terms in the sequence? I don't know. But the sequence converges, so I can compare them to the limit point. Okay, so xn minus xm, I minus x plus x, I haven't changed anything. I add 0. This is less than xn minus x minus xm. Okay, so if I choose my epsilon bigger than 0, such that when I go farther down the sequence than capital N, this is within epsilon and this is within epsilon, then the whole thing is within 2 epsilon. Or I choose my N, this is epsilon over 2, epsilon over 2. These things get close together, okay? So this gets small when N gets large, this gets small, then gets large. The sum of 2 small things is small. So this goes to 0, N and M goes to infinity. Formal proof. Repeat the steps that limits of sequences are unique. It's the exact same proof, just change the variables a little bit. Okay, so there before we had x minus y, and then we had xn minus x, and we had y minus xn. It's the same estimates, exactly the same estimates, okay? So I won't bore you with repeating it. But yeah, if a sequence converges, then if you go down the tails of the sequence, they have to be clustering closer and closer together. So this is a necessary condition. Now, what would make the world an amazingly beautiful place? If it were also sufficient, could it possibly be true that all Cauchy sequences are convergent? Could that possibly be true? Could the world be that beautiful? What do you guys think? Is the world a beautiful place, or is it dark and lonely and scary? Nobody wants to commit? It's beautiful. The world's beautiful. So, okay. The second row says the world's beautiful. How about the third row? Anybody going to commit? Dark and ugly? It's beautiful also in row 5 or row 4? Okay. So that's the big kahuna, the question. Do all Cauchy sequences have limits? Okay. Well, I'm here to tell you that the world is a dark and lonely and ugly and scary place, okay? And you got to toughen up to survive in it, okay? So, but the fact is it's almost true. It is like really, really almost true. So it's so close to being true that for most engineering problems, you've got it in the bag, okay? Isn't that a good thing? But it's not true enough times that you can find plenty of papers that screw this up. So you have to be careful when you're reading the engineering literature, okay? People forget this, that it's not, the world is not this beautiful place where every Cauchy sequence has a limit, okay? So, yes, unfortunately, not all Cauchy sequences have limits, okay? So we'll do one counterexample, and then we'll talk about the flip side of it, like why am I so excited that this is like almost true and it's very useful for engineers, okay? Why am I so excited about that? So this is just the warning that it's not totally true, but it's pretty close. So let me paste in my example. Oops, okay. No items match your search. Really? Okay, so it's in here then. Cauchy-Schwarz, Cauchy but does not converge. Okay, that sounds like a good one, huh? Okay, looks like I need to have it all in one page. That'll work. Okay. Oh, come on. I'll fix you. Flatten. Yes, you're not moving ever again. You're embedded into the PDF. Okay, so This is what we're going to do. We're going to work in an infinite dimensional vector space, the set of all continuous functions on the interval 0, 1. Okay? And the norm is this one norm that we've used, the integral of the absolute value 0 to 1. And everything here is super well defined because if a function is continuous, its absolute value is continuous, and continuous functions over bounded intervals have convergent Riemann integrals when you do the limits and all that kind of stuff. So everything here works. Riemann integral works, etc. We haven't defined continuous carefully, but I'm using your intuition for now. Here's the sequence. Let me show you the picture and then the formulas up above. So here's my interval 0, 1. Here's a half. I start my sequence at 2 instead of 1. So I go a slope from 0 to 1 with slope a half, with slope 2 here, okay? Slope is 2, the slope is 3, the slope, this should be the slope. Okay, the interval here is, see, this is starting out at 1, this is starting out at 1/2 minus a third, so this should be 1/6. This is starting out at 1/2 minus 1 over n, and so this is getting closer and closer as the slope gets bigger and bigger. So the slopes here are labeled wrong. I didn't notice that before. That slope is 2. That slope is 3. This slope is n. Okay, so these are continuous functions. Continuous rises up over this distance 1/2 minus 1 over n and goes flat. Okay, everybody see what the functions are? You can check the formula. It's not so interesting. Okay. Now, if you had to guess what this function is, what this sequence is approaching, it would be this, okay? And notice we don't put the straight line here because then it's not a function. Function needs to associate one value to the point to half, okay? So there's actually a solid circle here, and then when you go to just to the right of here, it jumps down, okay? So it's 0, 0, 0, open interval a half, and then closed half, it's equal to 1. Okay, so that looks like what it's approaching. Is it approaching that function in this norm? Okay. So, now, if that's the case, you can see we have a problem. This function is not continuous, and so it doesn't belong to x, so I can't even talk about it as a limit. So you see, I've got a Cauchy sequence, maybe. So when you check the one norm, it's the one norm of xn minus xm is the area of this little triangle right here. That's what the one norm is. So as you go farther and farther over, this triangle is getting area really, really small, okay? And the area of that triangle is in fact 1/2, 1 over n, and 1 over m. So this sequence is Cauchy, but there is no continuous function for it to converge to. So the sequence is not convergent. Bummer. Okay? So, Cauchy sequence. Our norm space is the continuous functions on 0, 1, and we put the one norm on it. That does not have a limit. In x equals c 0, 1. Okay? Darn. Okay. There's my sequence. That's what it's trying to converge to. That is not a continuous function. In this norm, the distance between these things is that little triangle I showed you, and you can go through and do the arithmetic, and that's what you get. So the sequence is Cauchy, but there's no limit point in this space. Okay, so what do you think? Now, if there were a finite dimensional example, do you think I would have given it to you? No, I'd make you go find it on your own. No. The world is a dark and crazy place, but your professor is a warm-hearted and loving old guy, okay? I'm the grandpa you always wanted to have, okay? That's me. So, there is no finite dimensional counterexample, okay? So, we will state that. There are no finite dimensional cases where your sequence is Cauchy and it doesn't have a limit. Whoa, okay, that's a whole bunch of stuff. I can do spaces up to n equals 600 billion trillion raised to Avogadro's number. I'm still good, it's finite dimensional, and I have Cauchy sequences have limits. As soon as I can show the Cauchy property, my limit exists. Now, here's a sequence. It's trying to converge to this function. And so what could I do then to fix this problem? It's Cauchy, but there's no limit for it. Well, what if I just make the space a little bit bigger and I start throwing in those limit points? Okay. And then I'm a good mathematician and I characterize what I get when I throw in the limit points, etc. Okay? Then all my Cauchy sequences will have limits. So that's where we're going. That's where we're going right now. Okay, so let me see how I want to state this. So proposition. Okay. Let this be a normed space. If X is finite, dimensional, then every Cauchy sequence has a limit in X. Okay, so the set of convergent sequences and the set of Cauchy sequences are exactly the same thing. Okay, so let's build on this with a definition. Okay, so this handles all of the finite dimensional things. There are no finite dimensional counterexamples. All the Cauchy sequences have limits. And what I mean by that, if something has a limit, it's in the space you are working on, okay? So it's not in something else. And to be clear about the something else is, yes, this is Cauchy. Yes, if I were to just throw this function in and I do the set of continuous functions plus this one and I take the span of that, okay, so I get a vector space again, then this sequence is convergent and this is the function to which it is converging, okay? So I had to grow the space, okay? So is this a convergent sequence? In this norm space, this is not a convergent sequence. There's no point in the set to which it is converging, okay? I'd have to build something bigger, and I will talk about that a little bit. So be super clear when you talk about converging sequences and you're given a norm space, the limits have to be in here, not in something bigger. Okay, I know it seems very obvious, okay, definition. Oh, it looks like it's a normed space is complete. At least spell it. Write it more clearly, is complete if every Cauchy sequence has a limit in the given norm space, okay? Just emphasize that again. Normed space, okay? A complete normed space X norm is called a Banach space. Okay, complete and Banach. There's a picture of Banach given earlier, okay? He didn't call them Banach spaces. He called them B spaces. All of them were used his initial of his last name. Hilbert, okay, so a Hilbert space is a Banach space, so a complete norm space where the norm comes from an inner product. That's David Hilbert's spaces. He called them H spaces, okay? On your final exam, there will be no G spaces, okay? Just to let you know. Okay, so norm spaces complete if every Cauchy sequence is also a converging sequence. Those are called Banach spaces. So all finite dimensional spaces satisfy that. And then there's whole catalogs of infinite dimensional spaces. There's whole catalogs of them. Okay. One more definition here. Let XX be a normed space S contained in X is complete. So we're just going to extend the definition of completeness to a subset of the space. The subset is complete, and it's the same thing. If every Cauchy sequence constructed from elements of S has a limit that is also in S. So this is just emphasizing the same idea I can't take my Cauchy sequence in X and have it converge to something outside of X and call that a converging sequence. No, the notion of a limit has to be something in X. And if I'm going to say a set is complete, all of the limits have to belong to S as well. Okay, so I can't take elements from S and say they converge to something else in X. That's not complete. They have to stay in S. They have to stay in S. Okay. And then I wanted dark. Big and bold. Proposition. X be a normed space. Okay. If S contained in X is complete, then S is closed. So completeness, to be complete, a necessary condition is that the set is closed. It's not a sufficient condition, but it's a necessary condition. Now, to be complete, I take Cauchy sequences in S, they have limit points in S. So S contains, by definition then, all of its limit points. So S is closed, okay? So that's why that limit point characterization of closure is interesting here. It makes it immediately clear completeness is closed, okay? If the norm space is complete, and S contained in X is closed, then S is complete. Okay, so we didn't start out assuming X has the completeness property. But if we add that, so X is Banach, then all closed sets, subsets are complete, and hence it's if and only if. So if X is a Banach space, then a subset is complete if and only if it is closed when you put A and B together. And then C, all finite dimensional subspaces of X are complete. Okay, so if I'm in a norm space and I take a finite dimensional subspace of it, like polynomials up to degree 27, can that set be open? Only if it's the whole space, because the whole space is open. But if it's a proper subset, no. It's a finite dimensional, the set of polynomials up to degree 27 has dimension 28, so it's finite dimensional. Hence it's complete, hence it's closed, okay? So finite dimensional subspaces of norm spaces are closed. They contain their limit points, okay? Cool. Okay. not on final exam completion of a normed space. Okay. So this is what I mean by the almost part, okay? I'm going to define a completion in a very rough idea. So let this be a normed space. Let me put a sub x on its norm. Then y is a completion of this if the following things hold true. A, y is complete. So it's Banach. This is where I'm lying just a little tiny bit, but x is embedded in y. X is a subset of y. And this is really the essence of the definition. And for every point in x, when you calculate its norm in y, it's the same as the norm in x. Okay? So the completion is going to be something bigger than x, but it's just a tiny bit bigger. C, the closure of x is equal to y. This is the closure of x viewed as a subset of y, okay? So this is not on your final exam. If this is hurting your head, just stop, okay? So normally I talk about convergent sequences in a norm space. I want my limits to be in the norm space, but now I'm viewing this as something contained in this bigger space, so I can seek limits in here. So this one can contain my discontinuous functions, okay? But x is very tight in here, okay? Nothing in y, everything in y is distance 0 from x. It's really tightly in there, okay? It fits very tight. So y equals x plus the limit points of the Cauchy sequences in x. So if you take that next functional analysis course and you do the actual construction, you build y from x by establishing equivalence classes of Cauchy sequences, saying they're equivalent. If you take their difference, it's actually converging to 0, so which they need to have the same limit point. And by that, you build y, and you induce a norm on y from the norm on x, and it's a beautiful thing. Okay, so this is what I mean by it's almost true that if I have a Cauchy sequence in x, does it have a limit? Well, in a slightly bigger space, it does. In this space, every point in it is distance 0 from x. Everything in here is a limit of something in here. Okay, and so that's where you need the extra mathematics, but if you formulate your problem in the completion of your vector space, then Cauchy is enough. It'll automatically be complete. And the fact is, every norm space has a completion. So. As a completion. Okay. So let's summarize just a little bit. If we did the continuous functions on 0, 1, but if you do the continuous functions on AB with the 1 norm, that is not complete. Okay. If I take the continuous functions and I put the max norm on there, that is complete. Okay, so there's infinite. This vector space, this norm space you will use in the nonlinear control class to talk about existence and uniqueness of solutions of differential equations. Okay. Okay, so let's go back to this, and then we'll do Newton-Raphson. Go back and have some simple fun, simple pleasures. Okay, continuous functions on 0, 1, C0, 1 with the 1 norm. Not cutting it. Here's a Cauchy sequence. This. So we have to throw this limit point into the set, and then we take the span. Okay. Of course, we can change where this broken point is, so we get all of the possible functions here, okay? And then we can take sums and spans, and so we get all of the different pulses at all the different points, and they can have, they will have finitely many, but as many as we want, that's finite, jumps that go up and down by taking linear combinations of those, okay? So that's starting to give you an idea that's got a lot of discontinuity in it, okay? So the problem is you get so much discontinuity that the Riemann integral no longer makes sense. Okay, remember Riemann integral, you take and approximate things by polygons, and then you take the limit as the width becomes 0, etc. You do the upper approximation, you do the lower approximation. When those two things are equal, then you have a Riemann integral. Okay, so its completion is called L1 of AB and requires Lebesgue integration. That means you have to do a course in measure theory. If you really want to understand that, but there's, like I said, catalogs and catalogs and catalogs of these things, and all these standard spaces that engineers want to work in. They're either already complete, like C01 with the max norm, or yes, it is a Lebesgue integral. Yes, you have to go off and learn what that means, but it's not It's not that hard. It just takes time. Okay? Ta-da! Okay, so let me see if there's questions. But the key point is mostly it's true Cauchy sequences have limits if we inflate the space just a little bit to its completion. In general, it's false. You're not required to know anything about completion, so the thing for you to know on the final exam, do all Cauchy sequences have limits? And the answer is simple, no. No, okay? If the space is complete, then by definition, all of the Cauchy sequences have limits. And then closed subsets of complete spaces are complete, and all finite dimensional subspaces of a norm space are complete. So this is the key stuff for you guys to know on Cauchy sequences, okay? This is the key stuff. Here, not on any final exam. It's just, to me, it's for the satisfaction of knowing I'm not very far away from having my Cauchy sequences have limits. And what I mean by not very far away, I grow the space just a little bit, and I get a space that is actually complete, okay? I can throw in the limit points, still have a recognizable norm space, and then Cauchy is necessary and sufficient for convergence. Okay, so now that's going to allow us to spend time on algorithms. And so let's just talk about one concretely. Newton-Raphson. So we're looking to find roots of y equals h of x. Okay, so we're going to suppose the function is reasonably smooth. It has a derivative that's continuous, and the determinant of that is non-zero. Because I'm going to be inverting this Jacobian in a little bit, okay? So that's our assumption. Our goal is to find a root. Not all roots, a root, okay? The approach is to try to construct a sequence. What you really want to do is show that the sequence is Cauchy because we're working in Rn, so it's complete. We just need to create Cauchy sequences, actually. Okay? Now we want this sequence to have the property, though, that its limit, if it does exist, is actually a root of our nonlinear equation. It solves h of x minus y equals 0. So it's a root or a solution of the equation. And so I'm just going to show you the little simple idea that Newton, and then Newton just did the scalar version and Raphson did the vector version of Newton's algorithm. How do I generate the sequence? So I'm going to start at some point xk, like x0. I'm going to perturb it and generate the next element in the sequence. That's all the idea is of Newton-Raphson. And I'm not currently at the root, but I'd like to perturb it in a way that I'm close to being the root, is the intuitive idea. Okay? So I'm not at the root. I'm going to perturb it such that I'm at a root. So how should I choose this perturbation to generate the next element? And the whole idea is just Taylor's theorem. Is that we linearize the equation about the current estimate. So it's the constant term plus the linear term. And then we throw away all the high order terms If this is small, that's a valid assumption. If it's big, it is a terrible assumption, and this thing will just iterate off to infinity or something, okay? So we'll talk about that in just a second, but this is the idea. So we set up this linear problem to choose delta x, and so we just say that's 0 now. And so this is equal to, we bring stuff on the other side, h minus y with a minus sign. And so delta x should be the inverse of the Jacobian times h of x minus y, minus sign. Okay, so just linearize using Taylor's theorem. Okay, so when can we expect that delta x can be small and hence the higher order terms will be negligible? Well, that's when we're starting out near the point, okay? If we're far away, Newton's algorithm doesn't tend to work very well. So you need a decent guess. But you just plug it in, and then there's xk plus 1, and that's the famous Newton's algorithm, missing a parentheses. Life is hard. Okay, now the problem is often if you're not very close to your initial point, this will be really, really big, and hence the whole basis of your algorithm is actually false. And so people introduce a scaling factor in here that's small, say 0.1 or something, and it's called the damped Newton algorithm. So this is step size control. And if you notice, this looks a lot like an Euler integration of a differential equation. This is delta t, okay? This is f of x. When I teach the nonlinear control, I do the differential equation, you get Newton's flow, and then you can start proving global and semi-global properties of this algorithm, okay? So that's pretty cool, using Lyapunov functions. Okay, so there's the Newton-Raphson algorithm, and if you don't use step size control and you start far away, it will systematically fail. Oh, I don't need that, it's there. Thought I made a mistake, but I was wrong? Yep, okay, good. I'm just going to reformulate this as where it's looking exactly like iteration of a mapping that I just keep reapplying this mapping over and over and over and over and over again. We're going to study those. They're going to be called contraction mapping. It's the contraction mapping theorem. And there's a key notion called a fixed point when we do that on Thursday. And a fixed point means it's an equilibrium point of the dynamical system associated to the mapping. xk plus 1 equals p of xk, that looks like a open loop dynamical system, okay, in discrete time. And this is just an equilibrium point of it, okay? But that's called a fixed point of the mapping. And let's just note that fixed points are what we're looking for because I replace p in here. I get rid of the x stars, so I have 0 equals this. This matrix is invertible. Epsilon is not 0, so this thing is 0 if and only if this part is 0, which means I have a solution. So fixed points and solutions of my equation are synonymous. And so the problem we're going to look at on Thursday is we're going to look at general equations like this and ask, is there a simple condition for when the solutions get closer and closer and closer, the iterates get closer and closer and closer together? So I generate a Cauchy sequence, and then if I'm in a Banach space, I have a limit. So Rn is Banach, so I would have a limit. So that's what we'll do on Thursday. So contraction mappings, and that's what Newton's algorithm is. It's a local contraction mapping. As it's given here, it is far from global, and it can't be if you have multiple roots in your equation, okay? You'd have to rule out the possibility that it's y equals sine of x and you're looking at y equals 0. I can find a lot of solutions, okay? That's the problem. Okay, that's it. Thank you.